Welcome. This is a background class on stochastic differential equations, continuous time mathematics. This is very useful in asset pricing. It's a branch of math that seems formidable, but in fact the basic tools you need are pretty simple. And that's what we'll go over. I assume that you've read the notes, and many of the derivations are in the notes. If you feel like you're not following the algebra, stop, go over how the algebra works. Diffusion models. That's what we call the kind of model we're looking at. Why? This is what a stock price typically looks like. Stock prices go up and down, and they jiggle a lot. They're random. We don't know what they're going to be. We need a convenient mathematical model for something that's random, that we don't know exactly where it's going to go in the future. I'm going to base this off discrete time. So I assume you're familiar with discrete time difference equations. So let me remind you the kinds of things you know how to do. In discrete time, we build up processes for something like a stock price. We start with a building block, epsilon, IID. I'll make them normal. They don't have to be. They will be in continuous time. Mean zero, unit variance. That's our building block. It's the easiest example of a stochastic process. We build up more complicated things from that. So the AR1 is your most common, easiest example. We build up the process X from these innovation epsilons through a difference equation. You've seen how to do that, and you know how to solve the difference equation. That means going from this differential representation, if you'd like, back to how xt depends on all the previous shocks. You know how to write a difference equation, solve the difference equation, and then characterize the moments. As of time t, what's the mean of x going forward? What's the conditional variance of x going forward? You know how, from that representation, to find the sequence of conditional means going forward and conditional variances. This is a plot of what an AR1 typically looks like. There's history. It's persistent. If it's high, it stays high for a while. And then I've plotted here the conditional mean and the conditional variance bounds, which are the things you know how to calculate. So from where we are today, you know how to make forecasts, and you know how to assess the uncertainty. Our job is to do exactly like that in continuous time. The ideas are all the same. We just have to write down a little math and think about it. Step one, we got to find the building block, the thing that's the analog to the epsilon. Step two, how do we take that building block and construct more interesting series out of it? Our basic building block, let's start with, is the random walk. It's easier not to start not with the epsilons, but with the sum of the epsilons. So z, the random walk, is defined as the partial sum of innovations epsilon. This is still discrete time. So that's how a random walk works in discrete time. And if you define a random walk like that, you can find its moments. You know its mean is 0, and its variance is t, the time that you've let the random walk expand. Random walks walk randomly. They kind of go like this, wander around, go up and down. That's a familiar discrete time process. This turns out to be the useful thing to take to continuous time. So this process has a mean 0 and a variance t. Let us define. Don't you love it when we say let us? It makes you sound like a mathematician. Let us define the continuous time version of a random walk, a Brownian motion, in exactly the same way. It is a process where its difference, zt plus delta minus zt, just like that, is a normal with mean 0 and variance delta. The variance is the same as the horizon, just as the variance here is the same as horizon. But here's the key. Delta can be any number, not just an integer. This is how we go to continuous time. So that's our basic definition. The Brownian motion, its increments are normally distributed. It's a process whose increments are normally distributed and whose variance increases with the time horizon of the differences. Now, from this, you know how to go back to the epsilons. You sort of take a first difference. What's the corresponding first difference operator in continuous time? It's called dz. So you'll see all over the little d operator, dzt. And it's defined simply as, let's look at the forward difference. dzt is, let's look at how much z changes. The forward difference at time t is the tiny forward difference, the teeniest possible forward difference. I put the limit in quotes because I'm not going to do all the mathematical niceties, but that's the way to think about it. This operation is just like saying epsilon is the forward difference of the z's. dz is the forward difference of the z's. Now that's all simple, but it has some remarkable properties. First of all, dz is of size square root of dt. What do you mean? Let's just look at it. The variance of zt plus delta minus zt is delta. That's how we defined it. Therefore, the standard deviation is square root of delta. And what does that mean? That means if you're looking at z at any time and you're thinking about what it's going to do forwards, the typical size of deviations is the square root of how long you look out in front. Well, standard deviation is square root. Typical size is square root. That means the typical size of a dz is the square root of dt. That's a big number when dt gets very small. From that, all sorts of strange and interesting properties follow. This typical size being square root of dt means that the z function is continuous but not differentiable, right? Because its size is square root of dt. That divided by dt is infinite. So it's always moving up and down infinitely fast and can't be differentiated anywhere. Kind of fun, isn't it? Another property, it's random no matter how closely you look at it. If you look at 10 milliseconds of data and expand it, it still looks random. It's always jumping up and down. It's fractal in that way. Fascinating process. Now, from that ingredient, what do we know how to do? What we're interested in doing is taking moments, as we did here. So what's the mean? This ET of dzt. Now, that looks weird, but remember, dzt is a forward-looking difference. So the conditional mean is 0, just as the conditional mean of the epsilons is 0. What's the variance? Well, the variance of dz is the mean of dz squared. dz squared, if dz is square root of dt, dz squared is dt. So the variance is dt. Variance is the same as the time horizon. Again, that's where this idea that dz is the size of square root of dt means dz squared is the size of dt. Don't forget that. dz is square root of dt in size. dz squared is dt. You'll use that all the time to simplify expressions. So that's our definition of the basic building block. The basic building block was epsilon in discrete time. Our basic building block is z and dz in continuous time. And it works exactly the same way, just squished down to very small time intervals. Our next step is to build up more complicated processes from these building blocks. That's called a diffusion. What did we do in discrete time? Here's a simple example. We took the x's and we formed a diffusion from x by adding up the z's, as we formed the AR1 by adding up the z's. Let's do the same thing in continuous time that we did in discrete time. So this is an example of how you form a random walk with drift. It's a random walk, but the mu allows a drift. How could we do that in continuous time? Well, same, right? Once you've written that, it's obvious. You let dxt on the left, mu times dt is the drift term, and sigma times dz term is the shock term. What are the properties of a random walk with drift? Well, et of dx, the expected value of that is just mu dt. The expected value of dzt, is anyone listening? That's 0, right? So the expected value is just mu dt. What's the variance? Well, the variance of dx is the mean of dx squared. That's just sigma squared dt. dt squared, that goes away. dt times dz, that goes away. dz squared is dt. That's the only term that stays. So we know how to find the mean and variance of the diffusion process. We're here to do finance, aren't we? The simplest and most common model we use for stock prices is a geometric Brownian motion. It's exactly the same idea, but we let dp over p be the object on the left side. This is the change in price over the price. That's the percent return. Let's model the percent return as something with a drift, maybe 5% on an annual basis, something with a variance or diffusion, maybe 10% on an annual basis. This is our basic model for stock prices that we'll be using all quarter long. A little more complicated. Let's do something like the AR1. So here was the AR1 in discrete time. xt plus 1 is rho xt plus a shock. We want to turn that to continuous time. We need a dx on the left. How do you do that? Well, let's put a dx on the left and take out another x on the right. Translate to continuous time, dxt equals, we tend to call that phi, not 1 minus rho, that's just what everyone uses, but a negative number times xt dt, and then a shock term. Isn't that the natural way to write the AR1 in continuous time? Once you've done that, you know how to find its mean. The expected value of dxt is that term. The variance of dxt is that term. Sigma squared dt. You know how to find the mean and variance at least one step ahead, looking a little bit ahead of the AR1 process. And like our AR1, if the level of x is very high, that means it's going to drift down, just as I showed up with the AR1 up there. More generally, how do we form diffusers? Here's the general recipe. You can just do like this and get as complicated as you like. The dx, the changes, have a drift term. This we call the drift. The drift term that says how is it drifting up or down at rate dt, and it has a diffusion term which says how it gets shocked by the shocks. So that's how we take the building blocks and turn them into more interesting processes with all sorts of persistence and other dynamics. What have we done in this first lecture? We've defined the Brownian motion and the change in the Brownian motion. These are the basic shocks that we build things up with. We learned this fascinating property that dz, the shocks to Brownian motion, are order square root of dt. We're going to have to rewrite a lot of calculus to handle that, but it's not going to be so hard. That means that dz squared is dt, so we have two sort of calculus-like terms with us. We've learned how to build more complicated processes, x's from z's, by these diffusion processes. And you've learned how to find moments. You've learned how to find the drift and diffusion, what's the instantaneous mean and variance of a diffusion process. See you on the next video.